Begin with, and then a third after tea. So the first session begins now. The title's up there, and the speaker's ready to go. So please, Vladimir, take it away.
Thank you very much. Great honor for me to be a speaker at this distinguished institute, distinguished program. So the title is Craik-Leibovich Equation or Dynamics, Distinguished Limits, Drift, Pseudo-Diffusion. And there is my name and two affiliations I have. So I am not exactly from the area of water waves, but still I have some interest and results related. And I call the area I am in generically vibrodynamics. This is a self-coined term by me and Professor Eulerian long ago, and this is now my area. And what I want is to attract attention of participants to kind of generality, universality, and also potential promising, potential to develop such classic area as drift and Craik-Leibovich dynamics equations. And I believe, and I will show, that those drift and Craik-Leibovich dynamics are applicable far beyond the water waves, but also could be, in my view, seriously developed for water waves. And what I count as my advanced is simplification and generalization of related asymptotic methods, which allow us automatically to move much further than many other people can do. So oscillating flows are very well known in all areas, not only in water waves. And of course, reason for oscillations could be oscillating boundaries, acoustic waves, and so on, many reasons. And the essence of my talk is kind of systematic presentation of asymptotic averaging results for oscillating flows, which are, I am sure, related to water waves. And those are just some results of oscillating flows. And maybe most familiar for water wave people, Lamgmuir Circulations, which you see on the surface of the lakes and see as system of parallel bands, parallel lines of foam or garbage, since of vortices are inside, under the surface. But generically, I consider oscillating flows as kind of a generic domain with generic boundary conditions which could be oscillating, not just water waves. And there are some examples. Oscillating flows could be generic like that. It could be, say, two pistons moving up and down, could be just rotating or oscillating solid body, or could be, say, acoustic wave. And generically, I consider such type of solutions which have some average of any amplitude and small oscillation about it, small oscillations about those. And the plan of the lecture is first to consider advection, drift, and pseudo-diffusion when velocity is given, so velocity is not satisfying to any equation, just a given function. Part 2, vortex dynamics of oscillating flows when velocity should be determined from the solution. And part 3, to mention at least some idea of generalizations of part 1 and part 2. So part 1 about drift. There are, of course, you read books Lam, Bachelor, many other, and Drifter there in a very in old presentation, like 19th century or even before. But the recent area of research, very active, called multi-scale method or two-timing method. I call it also vibrodynamics by some reason, allows to have a new view to this area. And contrary to many other approaches, I research drift using equation of advection of passive admixture, where v is any velocity, function of x and time, star means dimensional values, and a is just some passive admixture. And flow is supposed to have characteristic length and velocity, as well as characteristic frequency, means dimensional parameters, Struchel number is available. And in dimensionless term, generic presentation for velocity would be dimensionless velocity times scale of velocity, but still, because of Struchel number is additional parameter, it could be involved in the scaling everywhere in all places. And we consider a particular dependence of this scaling parameter on Struchel number with indefinite coefficient beta. And velocity, dimensionless velocity, supposed to be in two-timing presentation, like two-time scales. We have dependence on space, of course, but we have slow time dependence and fast time dependence, omega t. It means like for water, say modulated water waves are such examples, when you have frequency of wave itself and plus could be low frequency of modulations. But of course there are many examples of those type. And there are restrictions actually of smallness. Alpha should be greater than -1. It makes that tau is faster than s variable. You see, because this is fast variable, time variable, this is slow time variable. But also small amplitude of vibrations means this beta below 1, because omega times period should be small asymptotically, and small parameter here is inverse frequency or inverse Struchel number. So if we take the same advection equation in dimensionless form and also use chain rule for two mutually dependent time variables, and we have those derivatives with two small parameters, epsilon 1 and epsilon 2, which is asymptotically small when our frequency or Struchel number frequency goes to infinity. And our limit is in the plane of two small parameters which should go to origin. So it's typical PDE with two small parameters. And of course, to analyze PDE or ODE or whatever with two small parameters is a big challenge, because you have infinitely many paths approaching the origin, and the limits can give you different solutions, different presentations, different asymptotics. So, and one way to treat it is to consider S and tau as independent parameter. This is called two-timing method. And it can be justified for some special equations, but not for general case. So justifications are known, say, for ODEs and even for PDEs with convection. But of course, generically, justification is generally is different. But if we accept that variables s and tau, fast and slow time, are mutually independent, then this appears as a PDE with variables, special variables, as well as two timing variables. And of course, as in this situation, solution should depend on the same variables. And for further treatment, of course, we need to use to choose distinguished path, because there is a common mistake, not mistake, but mistreatment of many people to believe that equation with several small parameters could be generally treated. It is of course not true, because you cannot compare different terms on decomposition if comparison between epsilon 1 and epsilon 2 is unknown. But after you have chosen the path, you know, for example, that epsilon 2 is epsilon 1 squared, you parabolically approach and you keep some terms in the equations of the same order and so on. And what is the next? For applying this technique, we need to look for solution in the same two-timing form. So our solution represents functions of x, s, and tau, and with respect of tau, we consider them as 2 pi periodic, which can be generalized, but for this lecture I stick with 2-time periodic in tau, any dependence on s and any dependence on x. But for this situation we introduce standard average, because 2 pi periodic functions average over period, and function can be decomposed in average, not oscillating, and purely oscillating with zero average. Also we introduce integration over tau in such a way that average is subtracted in this tilde class. And next step is actually experimental mathematics. Nobody knows, and if you read any books, no one can say you how to look for distinguished limits, means for paths which produce valid asymptotic limit. It means you substitute, you can have zero term, first term, and closed system of equations as far as possible, if it is rigorous, regular procedure. There are different viewpoints, of course, in asymptotic analysis, but I consider this one. And of course, I also was looking for asymptotic for this distinguished path for this equation, and here I present actually infinite family when epsilon 1 is taken as epsilon, epsilon 2 is epsilon to n, where n is integer. N is integer, so to look for this equation, it's linear, parabolic, and cubic parabola, so on, approaching to the origin in epsilon 1, 2 plane. And solutions are we look for solution as standard series, and nobody knows how to find those limits, but you can just guess and try to calculate approximations. If you succeed, you're a winner. If your system of equation is not closed, for example, then you're a loser, and this is most frequent. For the majority of paths, it will be no, for vast majority, will be no asymptotic distinguished limits. And here I wrote distinguished limit 1, 2, 3, 4, which are characterized by different slow time scales. And first one is just generic average velocity plus oscillation. Second one appears when average velocity is 0, which is exactly like water waves. Dominating terms is oscillating, and average flow is correction, and so on. And this is drift, which will appear later. And after, if we have degeneration of drift, and next term of drift, we have other asymptotic paths. At least could be continued, and can be shown at least that first term is closed after 0 term, and approximation goes on. And what is the average equation? Of course, calculations are rather routine. You just substitute sum of bar function and tilde into equation, separate equation into tilde part and bar part, integrate them in 0 approximation, first approximation including zeros, and so on. No much reason to present them here. I just present some results. Say for distinguish limit 1, advection is going with average velocity, and some approximation due to waves appears in next terms, which will be the same as distinguish limit 2, which is, I emphasize, because this is a water wave program where main term in the given velocity is 0, and dominating term of velocity is oscillating, but next term could be not 0. So and slow time for this case is this one, and I was stupid enough to calculate 3 approximations, which is not easy. First one is very easy, and here the drift appears, and as you see, drift is of course Lagrangian property of flow, because this is a average velocity of material particle, and traditionally, say, if you take Lam or bachelor book, they calculate it as Lagrangian average in a way, but because it's calculated as dx dt is equal to velocity from ODE, here is entirely different approach for advection. So for 0 term and advective entity, we have just advection with drift. Second equation, advection with drift, first correction of drift. And already in the third approximation appears a diffusion-like term, you see. And for this particular presentation, velocity field is purely oscillating for simplicity, no average field, because with average field it's getting cumbersome. So, and this diffusion, average diffusion coefficient appears as Lie derivative of quadratic displacement. Psi is actually u sub tau, it's integrating over u. So, which is a mystery, which is still unresolved, why it should pseudo-diffusion, I called it, appears as a Lie derivative of this simple square displacement tensor, but it is. So 2 approximations thus drift, and third already for purely oscillating field without any average have a diffusion property. This is previous. This is distinguish limit 1. If you consider distinguish limit 2, where V0 is 0, drift is degenerating, this drift term is 0. What appears is the same terms are moving up. What is remarkable for those calculations, as soon as you calculated any approximation, all other approximation can be obtained automatically, just the same coefficients moving up or down. So in approximations. So if it is distinguish limit 2, it moved, no, it's still distinguished limit 1, because this is just formal describing of previous system of equation as one, previous system of 3 PDEs for approximation as one equation. Sorry for this. Distinguished limit 3 gives us advection with next approximation of drift for A naught, and diffusion appears already in the second approximation. Pseudo-diffusion. Okay, but all coefficients are the same as in previous approximation, just you see they moving up upstairs in approximations. And if distinguished limit 4, when two first terms in drift degenerated, then you have already pseudo-diffusion in the main approximation for passive admixture. And why it is pseudo-diffusion? Because property pseudo-diffusion are such that if you consider pseudo-diffusion matrix, it's always one eigenvalue is 0 and two other eigenvalues are opposite signs. So this is operator like xx derivative minus yy derivative, like hyperbolic operator in space, always, which is strange. And how to do with this diffusion, I don't know. This is subject for further research, and if everyone wants to participate, how mathematically you have, say, simple diffusion equation, but instead of Laplacian staying hyperbolic, what kind of solution it is a mystery for me, and I saw very controversial paper in literatures, extremely controversial. But another, of course, interesting situation here, that for each limit you have not one solution, but infinitely many solutions, because you just fixed dependence between epsilon 1 and epsilon 2. So, but it is just one equality for two parameters, you remember, beta and alpha, and therefore you can exclude one of them, say beta, and express in terms of alpha, and as a result, actually each distinguished limit produces infinitely many solutions, and they're different by scales of slow time and by amplitude. And what kind of example could be, if you take physical time, slow time, then you should use a small parameter 1 over square root of omega, and your scaling velocity, omega, you remember, the same as Struckel was, is square root, which is in many people who are considered from physical viewpoint rather artificial. But this is a physical slow time. But if you wish to consider physical scaling for velocity without involvement of Struckel number, then you have slow time t over omega, not t. And this is a confusing point for many people. It's kind of interesting feature of this asymptotic consideration, in addition to infinitely many solutions for any distinguished limit, and in addition to all I mentioned before. And examples could be numerous here. For example, you can consider just superposition of sine and cosine with arbitrary coefficients, and you can calculate everything, and any value, any function of P and Q gives you something, because here oscillating field is given. And P and Q are related to drift, and actually system is so much underdetermined that for given drift you have infinitely many P and Q's. So it's another example is of course just Stokes drift, standard from Lam, a bachelor formula in dimensionless form. You have this dimensionless field. Drift behaves like this, horizontal, and pseudo-diffusion appears as this this matrix. It's actually eigenvalues 1 and -1, and if you write it as a PDE, it is a very strange PDE for moving of advection with in accepted notations. So if you have a spherical acoustic wave, then it goes similarly, would be drift. First correction 0, second is not. But drift will be like from point source. If you have just acoustic spherical symmetric wave, then the drift will be a point source, means you will have kind of bubble in center, for example, increasing if it is physical, and so on. And diffusion, this is one-dimensional problem, and diffusion for this case appear as ordinary diffusion, because this pseudo-diffusion appears for 3D and 2D as hyperbolic type operator, but for 1D it appears as ordinary diffusion. So a weaker drift could be related, constructed very simply. For example, to kill drift in zero approximation, you just need to take tau and 2 harmonic. Then first term for drift will be 0, and any such field will give you other types of drift. And there are many questions what kind of drifts can appear in various physical applications. So the result for drift, first that it's strictly Eulerian approach in our case, that we have 2 independent scaling parameters, which is essentially inverse frequency and amplitude. Infinite sequence of distinguished limits has been discovered, but you can discover other limits if you are lucky, and will be different solutions, of course. Some results are presented, but each distinguished limit gives one parametric family of solutions. Pseudo-diffusion is a mystery, appears as Lie derivative of square displacement tensor, and how it appears solution mathematically, I have no idea. Of course, methodologically, this area is a classification of kind of entire story about drift, one way to classify it, asymptotic solutions related to drift. And last sentence, we do not use any additional assumptions except 2 timing and of course existence of 2 small parameters. So this is part about drift, where velocity was given by us. So, but if you add, say, Euler equation or Navier-Stokes, could be something else. And second part is about Craik-Leibovich equations, where velocity is not given, but should be discovered from the solution, calculated from the solution. And for simplicity, again, I consider only standard inviscid fluid dynamics of incompressible fluid. Again, the characteristic parameters is velocity, L, and frequency. And this is already dependent time scale. And we introduce dimensionless parameters and equations. And of course, we have again 2 small parameters. One of them is ratio of fast time and slow time. And fast time is just sigma t. Here sigma is frequency because omega is busy occupied with vorticity sigma is frequency, so fast time, but tau, slow scale of velocity is unknown. And this is another mystery of all this approach, because for each distinguished limit you have different slow time. You see, and after you're lucky to discover some distinguished limit, you automatically describe the order of this small parameter. Okay, and again we have actually difference between vorticity equation and scalar formal difference. Scalar advection is just vorticity is vectorial admixture, but it's also not passive. It's velocity vorticity is curl u as additional equality. But still, in terms of small parameter, they are the same. Two small parameters, ratio of 2 time scales, and amplitude of vibrational part of oscillation. Vibrational, but not average part of oscillation. And again, we consider asymptotic limits in the space epsilon 1, 2 to the origin. And there are also some number of asymptotic paths, also of integer type, I have discovered. But here I wanted just to present this one, which leads to Craik-Leibovich, which in my view is a historic step in fluid dynamics. So Craik-Leibovich is this one, when this epsilon 2 is square of epsilon 1 and appears extremely in a very simple way. And again, how to discover distinguished limits, it's only method of trial and errors available. You can guess and you can fail or succeed in asymptotic, in obtaining of closed system of equations. It's like, say, problem of turbulence. Of course, which is much harder, but if you try to close system, you are usually unlucky. And here is also situation is simpler, but very much the same. And Craik-Leibovich limit, fast time is sigma t, and slow time is t divided by sigma for some reasons which could be explained. And equation is like this. It's very much like equation we considered for passive A admixture, but here additionally, of course, vorticity is curl of u. And again, we take two timing assumptions that tau and s are two independent time variables, and solutions should be of these forms. And we are looking for standard series. And after substitution, we should here, in order to obtain what Craik-Leibovich did, we should just take that major mean field is 0. Because if major mean field is 0, we go to another distinguished limit, which was number 1 in my list. This was number 2. They will have different slow time scales. Then in 0 approximation, we have just potential field. It just follows from equation for vorticity. For vorticity, that field should be potential. It's automatically, the only assumption is that average flow in main approximation is 0. And after you go ahead with approximations, and only step number 3, epsilon cube term, produce the equation which in average gives you the famous Craik-Leibovich equation for the first approximation of the average vorticity. Because 0 approximation we accepted ourselves by force as 0. So in main approximation, flow appears as potential, but in first approximation, this what appears as Craik-Leibovich equation, this is commutator, which is the same as curl of omega 1 cross this standard equation for vorticity, except vorticity is frozen not to the velocity field, but velocity plus drift. Velocity plus drift. And for drift, we have very general formula. Drift can be calculated for any given velocity field, say for acoustic wave, or field generated by boundary conditions, and so on, say oscillating solid or wave or whatever you can resolve. So this is a very simple procedure which I should attract your attention if you take a book by Alex Craik, famous book on water waves, internal mainly waves. Those equation is derived by generalized mean theory, and it is quite a serious derivation. And here the derivation, achievement of this derivation, that this is accessible to any, in my view, undergraduate student, just few lines of expressions. But of course, from my point of view, from point of view of applications, to derive equation is not everything. In the average terms, you should also derive the boundary conditions, which could be any. For water waves, it should be, say, kinematic and dynamic conditions on free surface. And this is a much more difficult problem than derive equation of Craik-Leibovich. So with boundary condition, it's much more calculations. And they're so bulky that I'm not presenting here the dynamic equation for Craik-Leibovich, which, by the way, is unknown. Some people also have attempts. But for example, I present only, because Craik-Leibovich for vorticity appears as frozen vorticity to velocity plus drift. But if you take out curl, it appears as Euler equation with kind of Coriolis force, but it is not Coriolis because it's proportional to vorticity, not velocity. Yeah? It's kind of, this is Craik-Leibovich, but this is effective pressure, not full pressure. And a very serious problem is to calculate effective pressure in terms of average physical pressure, P, and it appears as quite a huge expression, and each term here should be taken from previous approximations. Say, actually, effective pressure depending on the same vorticity as U1. So it's kind of nonlinear dependence hidden inside. And of course, dynamical pressure itself, condition of zero pressure on free surface, would be rather bulky. But what I will do here is to write equation, kinematic equation. If on your, say, free surface or whatever solid surface is given as zero approximation plus the same epsilon as in your distinguished limit oscillatory term, then you can average it. And this is the same, because kinematic equation is the same equation as part 1 of my talk, passive admixture. Okay, passive admixture. And you can just took equation from first part of my talk, and you will see that actually passive admixture is advected with average velocity plus drift. In this situation, it's like that. And this is a big issue, say, in self-propulsion dynamics and so on. If you have, say, algae, and you wish to write average equation for deforming body, average equation could be written, it's not so difficult, but average boundary condition is very, very challenging in the same terms as average equations. And of course, people only say that, say, average velocity at average position does not satisfy the same equation as exact. Very often and so on. But actually it is possible just to derive average equation, and this is kinematic. Dynamic is also, but will be very bulky, and no one used it as far as I know. But this is simple, and you see it is very strange, because if your boundary is purely oscillating, not moving with slow time, this is motion of your boundary with slow time, and this is pure oscillation. Then you have leak condition. It means for W, this term is 0, you have this scalar product 0. This is just normal to your average boundary at average position. It means that you already kinematic condition gives you the leak, gives you that flow goes through your surface with drift velocity, you see, and this is very, very general result. So no leak condition for velocity plus drift, which can be expected, of course, from Craik-Leibovich situation when you have this kind of amendment. And this is one question about boundary conditions, which is too heavy to consider here, but this is very much open question. Another question here, of course, about next approximations. If you consider, you remember that Craik-Leibovich appeared in approximation epsilon cubed, which is already too much for many physicists, because physicists usually consider only epsilon square, and all after that considered as not physical. But actually Craik-Leibovich follows from epsilon cubed equation the solvability of those equations. But if you go to level 4, epsilon to 4, it will be also equations of next approximation in epsilon, which can be considered as small perturbation of Craik-Leibovich. So waves, linear waves or whatever, nonlinear waves on Craik-Leibovich equations. And this is approximation is in competition with, say, linearization, because some people did linearization of Craik-Leibovich, considered something. This is a different asymptotic limit, of course, but this is also equation which is not exploited, because it appears as kind of linearized equation, but with additional force, because omega 1 is already known from Craik-Leibovich, and this commutator, you have term commutator between omega 1 and this drift, which is essentially force terms. So it's equations which usually produce so-called circular term growing linearly, quadratically, or so on, but it's also open question. So this is Craik-Leibovich vortex dynamics once more. You have Euler equation with this fancy effective pressure. You have leak if only kinematic boundary conditions, so no free surface. If it is, say, deformable algae or solid body or whatever, only this boundary if it is, this is, of course, if effectively inviscid fluid, because if you use only kinematic boundary condition, then you should use more for viscous fluid. And what is additional situation which known for specialists but surprising for many newcomers, that for average you have conservation laws. For example, conservation of energy. For this Craik-Leibovich equation, you have, instead of U squared kinetic energy, it's U plus drift squared integral volume conserving by virtue of Craik-Leibovich equations and this no leak boundary conditions. So, of course, this does not give much, because you see this conservation law appears only when drift is independent on slow time, of course. So V naught squared term is just constant. So actually energy gives you U squared plus 2UV, and cross term could be of any sign. Okay, therefore you cannot use this estimation for a priori estimation for energy boundaries. So, but still, it could be useful, as well as, of course, you can track any other conservation laws, including helicity, momentum, angular momentum, and whatever you count, and they will appear for average equation under condition, of course, that your imposed oscillations do not depend on slow time. And this is a little bit about Lamgmuir circulation. It's now probably well known, but not for everyone. If you take Craik-Leibovich and just change notations, that they give you exactly equation of incompressible stratified fluid. Okay, and I don't know why it is unknown, but what situation appears that if you have a surface wave which is given, say, then your effective stratification is average longitudinal velocity, effective gravity is this one where u is x component of drift, and so on. So it's exactly mathematically the same problem, but in the class of translationally invariant average flow, not generically. And now part 3, my time is over, almost. Part 3, just we publish also a paper on acoustics when main approximation is any acoustic wave, even of large amplitude. And actually Craik-Leibovich equation is even better working for compressible fluid. Why better I can say, but to answer questions. Also MHD, also this kind of untouched area. Craik actually, I believe that this equation was subject of his PhD in 1974 probably, or something like that. But strangely, it was not attempt to generalize to many cases, including MHD. But if you do absolutely the same step for inviscid MHD, absolutely the same, you have drift appearing in the same way. Just average magnetic field is frozen into average velocity plus drift instead of average velocity, and with this system with Lorentz force, you have vorticities, like vorticity term similarly written, but it is of course not frozen, and Lorentz force is not affected, and all values here are average. And of course those equations are very attractive, say for looking for dynamo or looking for other interesting, say if solution is bounded and so on. Of course here is also pseudo energy conservation, which does not make up a bound, and so on. Also very much open question. So other generalization, viscosity and density can be routinely easily added. In the case, you remember that Craik-Leibovich appears in the term of epsilon cube. If your viscosity or density are order of epsilon cube, then it could be just routinely added to the equations. Say Navier-Stokes term could be added, but with those restrictions. If you wish to go to higher viscosity, it should be separate consideration. Should be a separate consideration. It's first paper Craik-Leibovich published 78, but it was after Craik PhD, which I saw once from him. Yeah, this is what I told you. And of course, what is attractive for mathematician or for person who are capable to do calculations, the drift for many situations could be considered as any function, which could be solenoidal, say, because to organize such fields of oscillations to produce whatever you want function for drift is very easy and can be shown that it is possible. So actually the analysis of Craik-Leibovich generically and MHD and many other stratified or viscous models could be such that you are looking for most dangerous or most interesting drifts to obtain some results, say magnetic dynamo or whatever, and if you succeed, then you can always reconstruct the oscillation field that produces required drift. So this step is not difficult. So, but in this it is always Hamiltonian average equations. This is can be discovered, but this is another direction to develop. Of course, there are many results because I told you that Craik-Leibovich is equivalent to stratification. You can move many results from stratified fluid to Craik-Leibovich, and some other possibility could be considered. And there are several papers we published in these directions, and red are directly related, green are not. It's just in vibrodynamics, which use the same method. And most recent appear studies applied mathematics about drift, in Arnold journals about vortex dynamics jointly from Proctor and Hughes. With Eulerian we did acoustics in Journal of Acoustical Society and so on. So this is, you can find, and this area in my view is very attractive because it has so many potential direction of mystery and potential results. And this is just thanks you for kind attention with mentioning my collaborators to discuss those items. Thank you very much. This is end.
Questions? Comments?
Okay, I probably misunderstood stuff as usual, Volodya, but I go back to part one of your lecture. Correct me if I get it wrong, but you said that if you choose a particular distinguished limit, coefficient n, epsilon to the n, etc., you work through it, and you have then a perfectly systematic way of generating higher approximations.
Yes.
Entirely straightforward, if heavy sometimes.
Yes.
But often or always, you end up with this pseudo-diffusion term on the right. Now, but the so-called pseudo-diffusion matrix has a negative eigenvalue.
Yes.
Which means that the system is hyperbolic, not diffusive at all, and therefore that suggests that any distinguished limit procedure that leads to this is not a correct one for describing a real physical phenomenon. I mean, this hyperbolic pseudo-diffusion, solutions are going to blow up. So
this is not proven. Even for ordinary equation like AT is equal UXX minus UYY, there are very controversial results you can find. It's not, mathematicians do not pay much attention to this, but physicists produce very confusing, controversial results. This is open question.
Okay, there exist such equations with particular initial and boundary conditions in which the solution blows up. If the physical system is clearly one in which, you know, the variables do not blow up, then that equation will not be describing them, and therefore, going back to the beginning, your particular distinguished limit may be would be not valid. So that, you know, you said on the one hand it's all very straightforward to derive all the different approximations, but on the other hand that it's a matter of choice how you choose your distinguished limits. And it seems to me that what we need is something to guide our choice rather more closely than you've provided.
This is a very interesting and key question, of course. You see, if you take, say, KdV equation or whatever equation which is obtained by some asymptotic methods, there are some results that if you go too far in approximation, you have terms growing linearly or whatever. And people are not confused with it. Some people are, some people not. So some people say that you can impose restrictions to kill the circular term in high approximation. But if you take a book like Kevorkian or others, they are more straightforward. They say asymptotic methods are such that they don't require to go for high approximation. If you consider just one good approximation like KdV, this is already achievement, and forget about next step, because next term in asymptotic series at the very beginning of Kevorkian book could be divergent, and they say this is normal, don't take it seriously. You see, there is a very controversial discussion among asymptotic people what to do in this case. But indeed, to writing of condition to kill, say, circular terms, there are quite many people trying to do it, but this is a very, very tempting problem, you see. It's actually a dream of many people. Actually, if you consider a wave, say MHD, Alfvén wave, consider approximation, we did it now with Proctor doing it. Circular term appears very quickly if you apply this, but they appear for generic zero approximation. So in order to, for first approximation, when they appear, it will be operator like Alfvén waves, and the right-hand side will be some nonlinear combination of zero approximation. And if you write equation to kill circular terms, it will be achievement, because it will be equation like Craik-Leibovich or whatever for zero approximation to make model consistent. And this is a very much frontier of research now for various in wave theory, for example. So this is a very, very interesting question, actually major question people trying to solve here, to understand.
Do you have formal asymptotic expansion, or you can prove remainder estimate?
No. This is probably it's doable for some simple, like first for some simple fields, but it was not my target. I just did first few approximation and saw in principle that this is recurrent procedure producing from previous approximation. Next one, which is doable easily, but to make a assessment, this is very, very mathematical, serious problem of justification. Justification I mentioned, say for some equation has been done, say for convection equation, it's Zinkovskaya and Simonenko, pioneering paper on 60, 67, very mathematical, from Rostov-on-Don. And for ODEs, the Bogolyubov-Metropolsky, as you know, this is the same stream as Bogolyubov-Metropolsky, but this is shortcut, of course. This is much simpler for ODEs. Of course, Bogolyubov-Metropolsky is only for ODEs, but here is only PDEs. For some ODEs it's available, yes, but for PDEs only, as far as I know, for convection. But this estimation of, but it is not as far as you said. What they considered that solution is solution of say, first approximation of average equation is close to solution of exact equation in some norm. In terms of this epsilon difference can be estimated in some norm via epsilon, but this estimation is valid only on a scale of time 1 over epsilon, not for infinite time. This is a typical result. So all asymptotics, they never proven for infinite time justification. Always the interval of time is inverse small parameter and only say for first approximation. So this is, of course, this is kind of Kantorovich general results were in this side, but I'm trying to stay away of pure mass. Yudovich, my collaborator, was very much involved and interested, but he passed away in 2006. And this topic is not, in Rostov some people still doing, like Livingstone doing, but not many people around here in Britain.
Okay, so thank you very much for stimulating.
Thank you very much.